So we're looking here at section 9B, which is linear modeling. This section will focus solely on linear growth and decay. You'll have a nice formula now to use with linear functions and models, and it will also give you a more concrete reason as to why in the last section we focused so heavily on independent and dependent variables. So sort of put all of both everything that we've talked about so far together, and this is one of that where I was talking about before, having a more efficient way of calculating linear growth and decay. These are your formulas here in this particular section. It should be noted that, however, that the majority of what you see here in this particular section is considered material that you should have coming into this class. Basically, DMA 50 is a prereq for this class, so really what you're seeing here really should be a refresher. I'll try to hit the highlights, and then we'll sort of go from there. All right. So here on this first piece here, it says, slope, and you're typically, hopefully, have I'm used to seeing that is represented by the lowercase letter m, and it is denoted as the change in the dependent variable, and remember, dependent variable were your y variables, divided by the change in your independent, which are your x variables. And generally what happens is that you're given two sets of ordered pairs, let's say x1, y1, and another set of ordered pairs, x2, y2. And if you wanted to find the slope between those two sets of points, you would do the change in y, y2 minus y1, divided by change in x, x2 minus x1. Another way to think about it is rise over run. After you've divided it out, simplify it as far as you can, that's your rate of change. Slope and rate of change are the exact same thing. They can be used interchangeably. However, rate of change always has the proper units with it, and I will speak more heavily about that in a few moments. Generally, slope you use whenever you are putting it in a model or an equation, okay? And that's essentially what we're talking about there in that next piece. Y-intercept, that's another piece of vocabulary that you should know. I should make the point back here with this formula for slope. You should memorize that formula, y2 minus y1 over x2 minus x1. Be sure you memorize that. Back down here to y-intercept. If you recall in the previous section, I gave you this formula. V equals negative 1,000 A plus 25,000. In that last section, we were talking about our independent and dependent variables, where the value of the car was dependent upon the age of the car. And we were mostly concerned about, okay, well, which is x and which is y. So you should hopefully recognize what's called slope-intercept form, y equals mx plus b. So if ever you're given something with different variables, you can always come underneath, and this is, okay, y equals negative 1,000 x plus 25,000. It clearly then tells you on the x-axis, age is going to be graphed, and on the y-axis, the value is going to be graphed, which is something we've already established. Where I was going with that, where else I want to go with that, is that the y-intercept is known as your initial value, and in a slope-intercept form, that's the b value. That's the number sitting out here on the end, and in this case, that 25,000. And that's the initial value. So essentially, in the terms of this problem, it was saying, well, the car was initially worth $25,000. And then the slope here is negative 1,000. That's always your number in front of your variable here. So a number in front of x after it's solved for y. So in our case here, it's negative 1,000. I'll have you interpret the slope in a few moments, and so for here we would say you always want to be sure that you state what's on the x-axis, what's on the y-axis, whether it's increasing or decreasing, and then by how much. So this is what I mean by that. Here my slope is negative 1,000. So a good interpretation of that would be that every year the value of the car decreases, because it's negative, by $1,000. Okay, so I've clearly stated, what's on the x-axis, that would be the age, so I'm taking every year, and I'm telling you, what's on the y-axis, the value of a car. I'm saying it's decreasing, and then I'm actually stating by how much, $1,000, okay? It should be noted, your book, for whatever reason, does y equals b plus mx. To be honest, it's the only math book textbook that I've ever seen, to write it that way. It's always been y equals mx plus b. So out of habit and what I've always known, and probably what you've always known as well, I'm going to continue with the y equals mx plus b format. Just recognize though your book just swaps it around on you. Um, all right, so a couple of things that you'll have to be able to find is how to find the y value for a given x value. So if I give you an x value, essentially you substitute that in for the x variable and solve for your y. Likewise, if you want to find the value of an x given a y, substitute that value in for y and solve for your x, okay? So, of course, we're going to go through all of these things here in just a moment, but I just wanted to, we'll talk you through here briefly to get started. Again, y equals mx plus b, that's your slope-intercept formula of a line. You should memorize that, okay? That's your linear model, okay? Y equals mx plus b, slope-intercept form, a linear equation, a linear model, all of those mean the same thing. All right, the procedure for finding the rate of change from a graph. Essentially, you know what, I think the best thing for me to do is to flip it over and let's just actually, talk you through with a concrete example. So let's go ahead and do that. Here, this is on the next page in example 1 is representing the length of a pipe in feet and then the installation cost. So obviously here that the installation cost is dependent upon how much pipe length you need, okay? In part A, it says, let's show a slope triangle on the graph paper. What the previous page was trying to say, or is saying, I should say, was that you pick 2 points. The 2 points do not have to be directly beside one another, but they should be points that you don't have to guesstimate at all, if at all possible. So like for example here, if I chose 15, I'd have to come up here and I'd have to say, is that 240? Is that 245? Is it 250? Versus if I were to choose the point here, 20, I know that's exactly 300. So that would be one that I would specifically choose. And then another good one would be to choose, I'm just going to keep on going up until I see, oh good, 45. So at 45, I can see, hope that's costing me $600, okay? So choose one that fall right in the nice crosshairs of your graph, okay? Then it says draw a slope triangle. So from here, you've got 2 options. You could draw this triangle, rise and run up top, or just so you know, if you wanted to, you could draw this triangle down here below. Okay, so either triangle is acceptable. I'm going to go in and erase that bottom one just so that I don't have so much going on here in my graph. All right, so let's get back there and that there. Okay, so that's what I mean by drawing a slope triangle. Now part B wants the rate of change. So rate of change is rise over run. You should be following that from the previous page. What you want to look at, okay, you want to go from, I usually find just going left or right is the easiest way to do. So what I want to do is rise. I rise until I'm in line with where my other point is. So in this case, starting from this point, I'm rising 100, 200, 300. So I'm rising 300. And then I run from that point. So it was a matter of, okay, I rose to get to here, and that was 300. And let me put a little different dot there. And now I'm going to run until I get on top of that last red dot. And so running there then from here is running 5, 10, 15, 20, 25. So I have 25 on the bottom. Because I went up, it was positive, and because I went to the right, it was positive. If you ever go down or you go to the left, those are negative. And so you would denote those with negative values. And so if in this case I can divide 300 divided by 25 gives me a nice even number, and so that is 12. It says I need to include my units. Anytime it asks for rate of change, you need your units. Think about what's on the y-axis. Y-axis is money, and this is pipe length. So this is $12 per foot, because you can see that your pipe length is measured in feet. So $12 per foot is my rate of change, or my slope, another way to think about that. Express this rate of change in words. So this is where I'm talking about those four things need to happen. You need to state what's on the x-axis, what's on the y-axis. Actually, tell me whether it's increasing or decreasing, and you'll be able to do that by telling me, by looking at this your rate of change and determining if that's positive or negative. And then lastly, actually state that number. So in our case here, since this is like 12 over 1, for every 1 foot increase in pipe length, the installation cost increases because this 12 is positive. So for every 1 foot increase in pipe length, the installation cost increases by $12. So again, always state what's on the x-axis, the y-axis, tell me whether it's increasing or decreasing, and then by how much. Okay, so I'm not going to write that out. It's written out on your form, on your solution guide, and I just said it. All right. Part B says using the graph, estimate the y-intercept. So this is where, you're definitely going to have to estimate here. It's not on a perfect number. It's obviously less than 100. I'm going to say 75, but like I said on the solution key, anywhere between 70 and 80 is really okay. So I'm just going to go with 75. Hit it right in the middle. Okay. So write in words the meaning of that y-intercept in the problem. So essentially, at that point, 0 pipe length has been installed, but you got $75. So essentially, the base installation cost is going to be $75. So I'm going to write this out. The base installation cost, abbreviate, is $75. Okay. Now, part F then says, okay, now with your rate of change, which is obviously, your slope, and a y-intercept, write in a linear equation to model the data. So if it ever says write a linear equation or write a linear model, we're always wanting you to go into y equals mx plus b format. So I'm going to go to my y equals. M is your slope. We calculated that back in part B, so there's your 12. X plus b is your y-intercept. You just calculated that back in part D. So 12x plus 75. It should be noted I could have written this as C equals ML, cost, C standing for cost of my pipe, my installation cost, and L being the length of the pipe. You can use any letters that you want to. I mean, personally, I usually go with the Y and the X because you're just going to start graphing at this point, but you can use other letters. Feel free to do that. And sometimes you still will see me do that. All right, in part G, it says we'll use that linear equation, or I'm going to write that above that, linear equation, or if it says use the linear model that was created in part F, okay, predict the installation cost of a 75-foot pipe. 75 feet is an X value, right? So I've got to plug 75 in for X because I want to find the installation cost, and cost, you remember, is your Y value. So using my formula, Y equals 12X plus 75, I know X is 75. I substitute everywhere I see an X with 75. And I just pop that in my calculator. 12 times 75 plus 75 should give you 975. This is what Y is. Y is installation cost, so let's put $sign in front of that. So we're talking about $975 would be the cost to put in 75 feet of pipe. Okay. Letter H is the flip side. Suppose now we know the installation cost is $1,500. Installation cost, that's being measured on the y-axis, so now we know that y this time is $1,500. How long was the pipe that was installed? So again, go back to your model, y equals 12x plus 75. I know that that y is 1,500 this time. And I've just got to do a little bit more work this time. I want to solve for x. So your goal is to get letters on one side, numbers on the other. Since 1,500 is sitting over there all by itself, take 75 over to join it. When you cross the equals mark, always do the opposite. So I subtract 75 from both sides. 1,500 minus 75 should be 1,425. That equals 12x. Lastly, you want to solve for x. Always divide by the number beside your letter. So you divide by 12. cancels out over there, just leaves you with x. 1425 divided by 12 should give you exactly 118.75. The problem told you to round to the nearest whole number, so we'll round that up and we'll say 119 feet. Don't forget your units in this section. Okay, so I'm going to flip it over. And you know what, example 2 basically lets you try one from top to bottom, sort of mimicking the steps that I just went through. So I will let you try example 2 at your pace. The only thing different in this one is that you can see here as you read this graph from left to right, it's decreasing. So you should find then in this case that your slope is going to be negative. It's always, you know, when you in this particular problem, when I'm reading this graph from left to right, my line is increasing. You know, read these graphs like you read a book. So from left to right, my graph is increasing. So my slope should be positive. On the next page, as you read this from left to right, this graph is decreasing, so my slope should be negative. And that'll be your biggest difference between what we did in the last problem. So I'm going to let you try that one. We'll flip it on over. Let's look at example 3. In example 3, it says the tuition, and C standing for cost, at a community college is calculated from the number of credit hours, H, a student is taking, as well as an additional student association fee. The calculation is based on the following formula. C equals 75H plus 50. So in here, in part A, they want the independent and the dependent variable. There's a couple of different ways that you can look at this. I mean, you know that C is your cost and H is your hours. You could ask yourself that sentence. The blank is dependent upon the blank. Or you could go with, you know what X and Y are. You know, that your X is your independent and Y is your dependent. And what I had said on the previous page is, okay, well, y equals, this is basically in y equals mx plus b format, it's just using different letters. That then tells me that x is h, my hours, so my hours are my independent variable, y is my c, and that's my cost. And now if you think about it, if you said your sentence, your cost is dependent upon the number of hours that you take, okay? Part B wants the rate of change. Rate of change is the number in front of your x. So in our case here, it's 75. I want to be sure, though, rate of change needs the units. So rate of change is the change in y over the change in x. So remember, this is your y, and this is your x. So my units then would be a cost per hour. So $75 per credit hour. I want the y-intercept. The y-intercept is just that lone number sitting out there. In our case here, $50. So that automatically, they've got like a student association fee and technology fees and stuff like that. So that'd be a base fee that every student had to pay. Okay. Let's see. Looking down at the next piece, it says that, well, how to make up an equation from a word problem. Rate of change and slope are the same, mean the same thing. Initial value is your y-intercept. You should be able to read certain problems and figure out, okay, well, this is what's changing, so that's going to be my slope. This is the initial start value, so that's going to be my y-intercept, and be able to put those in for yourself. This is where knowing those independent and dependent variables will be more helpful to us. So let's look at this next example in example 4. This piece up here talks about graphing it. I'm going to focus a little bit, instead of talking you through that, let's show you through that. In example 4, this is a luxury car valued at $45,000 depreciates at the rate of $3,000 per year. I want to give a function of the value of the car after t years have passed. Okay, so you got two variables here, value and time. So, let's think about that. Okay, what's independent and what's dependent? And hopefully you're thinking that the value is dependent upon the time. So I'm going to write that in. The value is dependent upon the time. I just paused just so that you could think about that yourself for a minute. The function then, okay, you know, the function, the model, the slope-intercept form, the equation, the linear equation, again, all mean the same thing. So I want the function then that would model this particular situation. It's depreciating at a rate of $3,000 per year. So, and it's a luxury car was valued at $45,000. So hopefully you would recognize then that it's you know, its starting value is $45,000 and it's depreciating. Here's my slope. So I can say then, if you want to do y equals mx plus b, I can say, well, y equals then negative 3,000 x plus 45,000. I had to put a negative in front of that 3,000 because it was depreciating. Or if you like it better, you can say the value of the car is equal to negative 3,000 t, you know, the age of the car, plus 45,000. It doesn't matter which letters you use, X and Y, V or T. I'm not too picky about that, okay? The next part is, okay, well, how do you actually graph then this particular linear function? So you know what's going on the x-axis. On the x-axis is that independent variable, the time. On the y-axis is your dependent variable, the value. So along the x-axis you have time, and it would be measured in years. And along that y-axis we'd have value, and we're going to measure it in thousands. There's a lot of different ways to do this problem. Since the value of the car is starting at 45,000, I could count by threes. That would be the easiest way to do it because my slope is 3,000. So that's the reason why you see on my solution key that I started down here at 3, 6, 9. Let me try to do this as precise as I can. 21, 24, 27, 30, 33. I know it's not, my handwriting's not that great, this pen, but what I'm trying to show is that in order to graph this, you always, whenever you're graphing a linear function, always start on the y-axis at the y-intercept. So I need to plot 0, 45,000. So I'm going to plot here at 45. From that point, this is my slope, negative 3,000. And if you don't have a number underneath it, there's an imaginary 1 sitting underneath that. And so what that means is this is your rise over your run. So I need to rise 3,000, but because it's negative, I'm going to go down 3,000. By me counting by threes, then going down just 1 unit is going down 3,000, and I run 1 unit. Because if you notice, I would definitely want to count years, you know, in whole numbers there, 5, 6, 7, like, and so on, like that. Okay, so at 1 month, then I'm down to 42,000. Get that there. And then for the next one, I would go down 3,000 over 1. Down 3,000 over 1. And I would just keep doing that, going down 3,000 over 1. There's a lot of different ways to do that. And I continue the graph on. You can see it better in your solution key. We'll flip it over to the next page. Let's look at example 5. It says here that a factory makes desks. The cost of running the factory is $700 per day plus $200 for each desk that's manufactured. I want to set up an equation and use it to find the cost on a day in which 36 desks are manufactured. So you want to take a moment and find your independent and your dependent variable. So you remember your x and your y. Just trying to reiterate that. Take a moment to think about that. Here, the number of desks would be my independent that are going to be manufactured, and the cost. The cost is going to be dependent upon the number of desks that I get to make, okay? Cost of running that factory. So my function then, always y equals, how much then is the the cost of the desk changing? So $200 for each desk, so 200x, and an initial cost $700 per day. That would be my function. Oh, just 700. Oops. So then in part, the solution part, okay, so I found my equation, and I want to figure out, well, how much would it cost then to manufacture 36 desks? Since x is your number of desks, then for x, I'm going to replace that x with 36. 200 times 36, add 700 in, $7,900 it would cost to manufacture those 36 desks. All right, I'll let you try example 6. It's really important that you get that one down. That's a common one to see. The next one down is also an important type of problem. I'll do example 7 and then let you try example 8. In example 7, what I recommend that you do is first, identify what your independent and dependent variables are, so you know what your x and your y is. You're going to pick 2 points and find the slope. Then you're going to use your formula y equals mx plus b, substitute in one of those points and the slope, and you're going to solve for your b, and then ultimately you're going to go back in and only substitute m and b, and you're going to have your slope-intercept form. So let's take example 7 top to bottom through those steps. So here it says in example 7, a well drilling company charges its customers by the number of feet it digs into the ground. Use the information below to find a linear model for the cost function. So what we're seeing here, that if a well that's 200 feet deep costs $1,300, a well that's 350 feet deep costs $2,200. So you can see here that the cost is dependent upon the depth. So if my cost is dependent, then I know then that my cost is my dependent. So that's my y. So then the well depth must be my independent, which must be my x. So once you know that, then you've got 2 ordered pairs here. Ordered pairs, remember, are always x comma y. So the first line tells you that your x is your well depth of 200, and its cost is $1,300. And then your second line tells you, okay, its x value is 350 feet for a y value of 2,200. All right, step 1 then says, okay, so we found our independent, dependent. If I've got enough room here with this pen. First thing you want to find is the slope. So find the slope, your formula, y2 minus y1 over, it's a minus up there, over x2 minus x1. So if you look at here, you've got 2,200 minus 1,300 over 350 minus 200. I just sort of took for granted there, but remember you can label this x1, y1, x2, y2. Okay. Subtract up top, you should get 900. Subtract on the bottom, you should get 150. Divide out, you get a nice even 6. That is your slope. Okay, so tuck that away in the back pocket. We'll need that in a moment. Second step, use the formula y equals mx plus b. Substitute in 1 point and your slope. So I'm going to first write out my formula, y equals mx plus b. Definitely substituting the slope you just found, so there's your 6. Then it says substitute in 1 point. So you have this point, 200, 1,300, and the other point, 350, 2,200. Use either one of them, but don't choose the x of this one and the y of that one. Okay, you pick a point and you go with it. It doesn't matter. Either one is fine. Me personally, I try to stay away from negatives. I'm going to go with this first one because they're nicer whole numbers. This one has a 50 in it. Not that that's anything grossly bad or anything, but this one's a little easier to work with. So I'm going to choose then this first ordered pair. So then my y value, I'm going to plug in 1300. I've already got my m. X is going to become 200, and I'm solving for b. Okay, so we know then that, and that's a 6. So 6 times 200, we can clean that up to become 1200 plus b equals 1300 still. I want to solve for b, so one step. Subtract 1200. Whatever you do to one side, do to the other. So b equals 100. So now you've got a slope and you've got a y-intercept. You're ready for your equation. Your model, like I said, the equation, the model, the function, whatever you want to call it. So y equals 6x plus 100. And you're good to go. Definitely recommend try example 8 below here so that you're good to go with that. Okay, let's flip it over to our next page. So far, most everything that we've looked at has been perfectly linear, but it should be noted that not all data is perfectly linear. This example below represents the number of beers consumed and then a person's subsequent blood alcohol level. And as you can, hopefully, imagine for yourself that, one person can consume 2 beers and have very little effect, and then lightweight, so to say, quote unquote lightweight, could have a much greater effect off of 2 beers. So with that said, then that there's a little bit more variance in my data, but ultimately there's a pretty good linear pattern going through here. Part A wants to know independent and dependent variables. You've already got a graph here, so remember independent's your x, dependent's your y, so you can see then x number of beers, y-axis your blood alcohol concentration. So I won't take the time to write that out. Part B says, we'll complete this sentence. As the number of beers consumed increases, a person's blood alcohol concentration also increases. That can certainly, despite someone's weight, that's definitely going to happen. Increases. A person's blood alcohol concentration also increases. Part C is a different piece here. It says draw a trend line on the scatter plot above. And essentially, the idea of a trend line is you want to try to go through as many points as you can. You don't want to try to play connect the dots, okay? So doing something like this, and I have definitely seen this before, don't try to connect all of the dots here, okay? That's not the goal of a trend line. A trend line is designed to roughly run through the middle of your data and connecting as many points as you can, but you don't even necessarily sometimes even have to hit through a ton of data points, okay? But you want to try to go through the middle of the data. So I'm going to try to shoot for something like that. Okay, that's a good trend line where I've got basically almost half my data points below me as half below as above. Okay, and I'm doing this freehand, so you could probably get even a better line if you were straight down on a piece of paper. Okay, part D says pick 2 points and find the equation of the trend line. Now here, since I've just said pick 2 points, this is where there could be a whole lot of variance. Let's all say that we're going to pick 2 specific points so that we are at least find the same trend line. I would definitely make sure that you did that on a test. Okay, I would be specific and say, okay, pick these 2 points. All right, so I'm going to say let's pick this point here, 4.05 and 8, 1.2. I'm going to pick those 2 points, 4.05 and 8.12. I'm sorry, I think I said 1.2, 0.12. It says pick those 2 points, find an equation of the trend line in slope-intercept form. So the equation of the trend line is very similar to what we just got finished doing. Equation of the trend line, like I said, I've been saying equation of the trend line, a model, a linear function, all of those mean the same thing. So the first thing, you've got 2 points. Hopefully you're recognizing then, oh, I got to find the slope. y2 minus y1 over x2 minus x1. So I'm going to have 0.07 divided by 4, which is going to give me a slope of 0.0175. Alright, so that would be my first step, find the slope. Second step, go to your y equals mx plus b. Substitute in everything you know, so you know your slope. Pick a point. It doesn't matter which one you choose. I'm just going to choose my first one there. My y is 0.05 and my x is 4 plus b. And I'm going to solve for b. So I'm going to do 0.0175 times 4, which is going to give me 0.07 plus b on that side. One more step, subtract 0.07. So then I should have b equals negative 0.02. Negative. Good. Last thing you need then is the equation. That's your y equals mx plus b. So y equals, you plug in your m, 0.0175x plus b. Since your b is negative, just go ahead and put a minus sign, 0.02. You can put plus and negative, but you can just go ahead and say minus 0.02. That allows you then, now that you have this equation, to do something very similar to what we've done before. So once you have the equation that you've created this time, you can use this linear model, exactly what we just found here, to predict a person's blood alcohol concentration. Remember, the blood alcohol concentration here is being measured on the y-axis, so you're trying to find y. When a person consumes 8.5 beers, that's your x. So substitute 8.5 in for x. So you'd be putting this in your calculator, 0.0175 times 8.5 minus 0.02, and you should find that they would have approximately a blood alcohol concentration of 0.13. And then lastly, in part F, again, use that same linear model that you've created to determine how many beers one person must consume in order to reach the legal limit of 0.08. So the legal limit, that's your blood alcohol concentration, that's your 0.08. So here's my model, y equals 0.0175x minus 0.02. X stands for the number of beers, that's what I'm trying to find. Y stands for the blood alcohol concentration, that's what I know. So 0.08 will go there. It's 0.08. Let me start over there. .0175x. You want to solve for x, so you want to get letters on one side, numbers on the other, so I got to get closer and closer to getting this x all by itself. So I'm going to take 0.02 to the other side, do the opposite. Since it's subtracting 0.02, you add 0.02. That's going to give me 0.10 or 0.1. You want to solve for x. Alright, so you always divide by the number beside your letter. So divide by 0.0175. And after you divide that there, maybe do a little rounding if you need to, you should get 5.7. X stands for beers, so be sure you put that unit there. So 5.7 beers would put you at the legal limit. Okay. Example 10 is exactly like what we were just doing, so that will allow you to run through one where the only thing you would have to do differently is you have to plot this data, but I think you'll have a good representation of what's there on the solution key. All right, that'll do it. Thanks.